Let's take a look at how to solve. We're going to look at 3 different kinds of word problems that occur pretty typically in linear equations. So we're going to look at solving linear equation word problems. And we're going to look at it with a particular approach. We're going to look at using tables to solve these. So this is one way that you might choose to organize the information in a word problem in order to be able to solve it. So for some context, I'm going to give us an example problem. The first example is that a contractor has 480 cubic feet of concrete that is 60% sand by volume. How much pure sand should be added to make a new mixture that is 70% sand by volume. So that's one type of problem that we might solve with this method that we're going to look at. A second type of problem might be something like a student takes out 2 loans totaling $12,000. One of the loans charges 4% simple interest per year, while the other charges I spelled that wrong, charges 10%. If the total interest in 1 year is $1,080, how much was borrowed for each loan? So completely different context there, but we're going to see that we can use similar techniques to solve these 2 different kinds of problems. We'll look at one more example. And in this example, a student leaves home to ride her bike to school. At the same time, Her brother walks in the opposite direction to his school. She arrives 30 minutes after leaving, or let's say, for the sake of simplicity, we're going to say a half hour after leaving. While her brother arrives 1/3 of an hour after leaving. If she bikes 7 miles per hour faster than he walks, and the schools are 6 miles apart, how fast does each travel, or at what rate? Does each travel? Okay, so again, 3 different problems, seemingly unrelated. We're going to see that we can use the same technique to solve them. The key here is that each of these relies on a formula that uses multiplication. So in example 1, this is what's typically called a mixture problem. And in a mixture problem, you're using the fact that the percent times the whole amount gives you the part. So we can see some multiplication in that formula. Example 2 is an interest rate problem. And in there, we know that our interest is equal to our principal times our rate times time. So again, we see some multiplication going on in there. And the last problem is a motion problem. So example 2 is an interest problem. And in example 3, we have a motion problem. And there, we're going to use is the concept that distance is equal to rate times time. So in each of these, we have a multiplicative formula. And we're going to use that multiplication to set up a table. So in our table, notice also in each of these problems, we have 2 things being combined in some way. In the first, we have a 60% sand mixture and a 100% sand mixture. In the second, we have 2 different loans being mixed together to make interest. In the last, we have 2 different people walking. So what our tables are going to look like is we're going to have item 1, item 2, and then often we'll have a total. That's not always necessary, but it can be. So we have something like that. And then we're going to have the various components of our formulas. So we're going to have something times something equals something across the top. And those elements are going to be they are going to come from the distinct formulas that we're using. You'll notice that the interest formula actually has 3 components. We would need an additional column if time is not equal to 1 year. In our example, it is. So the T part of that formula is going to drop out. All right, so let's look at example 1. So example 1 is our mixture problem. The 2 things we're missing, or mixing, not missing, are our 60% concrete mixture. And then we're adding to that pure sand. So those are our 2 items. And the thing we're making is an 80% concrete mixture. Right, was it 80? Oh, nope, 70%, excuse me. So those are our 3 rows. And our formula says we're going to take the percent times the amount of the whole amount, and that's going to give us the part. In this case, the part is the amount of sand, right? The concrete is a mixture of a couple of things, one of which is sand. When we multiply the percentage of sand times the amount that we have, that gives us the amount of sand. And so if we go through the problem, well, the 60% concrete mixture, that's 0.6 as a percent. We're going to write that as a decimal so that we can use it to multiply. And we have 480 cubic feet of that. Right. Our formula tells us that if we multiply those across, we are going to get the amount of sand. And so when we multiply across, what does that give us? 288, and this was in cubic feet, so now we know we have 288 cubic feet of sand contained within that concrete mixture. The pure sand is 100% sand, so we're going to put a 1 here, but we don't know how much of it we're mixing. That's the question. So when we multiply those two together, we just get X. Now, when we mix them together, this mixture is 70% concrete, so 0.7 is our amount there. We don't know how much we're going to end up with, but we do know that the amount we have is the 480 cubic feet we started with plus the X cubic feet that we started with as well. And when we multiply across, we get an expression that looks like this. All right, so far we've used the fact that our table, we set it up so that our table multiplies across. The other thing we're going to use when we do these tables is the fact that typically they add going down. Now, notice the rates did not add. Percentages are not additive like that, but the amounts added together and the parts added. So we don't ever mix anything that's a rate or a percent, or we don't add those together, but we can add amounts. And so what we end up with is, by adding this up, we know that 288, that was our 0.6 times 480, plus X have to equal 0.7 times 480 plus X. Oh, now we have an equation that we can solve. Right? The amount of sand in the 60% mixture plus the amount of sand we add has to equal the total amount of sand in the final amount, in the final mixture. So we have this equation here. And when I multiply that, what am I going to get? 336 plus 0.7x. And now I have a nice linear equation in x, so I'm going to move the 288 over, subtract that from both sides. That is 48 plus 0.7x. Then move the 0.7 over. 0.3x is equal to 48. And that is going to give me x is equal to, divide that by 3, and I get 160 cubic feet of pure sand. That's what I'm going to add. And we could do a quick check if we multiply that times, so if we add that, 480 plus 160, that's for 640 cubic feet total, times our 0.7 is 448, which that's not right. Oh, yes it is. Because we started with 288 feet of sand and we add 160. and add those together, and we also get 448. So the amounts of sand end up equaling each other. That's just a quick check. Okay, so we can do the same exact thing for our student loan problem. So here we have this one, we're going to use the same idea. So we have loan 1, and we have loan 2, and then we have the total borrowed, right? And each of those is going to have a principal amount, a rate, an amount of time, which in this instance is the amount we borrowed, or is 1 year, I'm sorry, and an amount of interest on them. And again, we're using the fact that those multiply across to set this problem up. Now, we know that the total borrowed was $12,000. So if we say that loan 1 is X, then we can say that loan 2 must be 12,000 minus X. That's the amount remaining. I'm doing that. There are ways to solve these using 2 variables, but I'm trying to just use 1 variable here. So I'm sticking with my X, so I have 12,000 minus X. My first rate was 10%. My second rate was 4%, so those go in there. Each of these was just for a year. So we just put a 1 there. Now notice we don't total the rates. It doesn't make sense to add those up. And because we're paying off these loans simultaneously, we're not totaling the time. But we do have a total amount of interest. It was $1,080. So now I'm going to, again, multiply across. I get 0.10x, and here I get 0.04 times 12,000 minus x. And I use the fact, once again, that our table is set up so that we multiply across, but we can add going down because the bottom row is a total column and totals always come from addition. So if I do that, I now have that 0.10x plus 0.04 times 12,000 minus x is 1080. I will go ahead and distribute. So that's going to give me 48 minus 0.04x is equal to 1080. I'm sorry, that's 480, not 480, not 48. That's 0.06x plus 480 equals 1080. 0.06x, subtract 480 from both sides. That's 600. Divide by 0.06. And I see that x is $10,000. X is $10,000. I also know that my other loan, so that represents my loan 1 amount. My loan 2 amount was $12,000, so this must be a $2,000 loan. I hope those were the numbers I originally used. Yes. All right, so that's a second way we can use the table. So the commonalities here are that we have 2 quantities that we're looking at, and that they each have a multiplicative formula that allows us to set up our columns as parts of that formula. So for our last one, we've got our biker and her brother, or cyclist, I guess. I guess she's not a biker, she's a cyclist. And our walker, her brother the walker, and here we're using the fact that distance is equal to rate times time. So if we put their rates here and their travel times here and we multiply those, we get their distance. We don't know either of their rates. We just know that hers is 7 miles an hour. I believe it was 7. Let me look back at what I wrote down. Yes, hers is 7 miles an hour faster, right? It makes sense that she should be faster cycling. So if we call his x, then hers must be x plus 7. alternately, we could call hers x and his would be x minus 7. She rides for a half an hour. He rides for a third of an hour. I'm actually going to use fractions there because a third is not a terminating decimal. And we multiply across. So I get 1/2 times x plus 7. When I multiply across there, I get 1/3 of x here. The other fact I know is that their total distance, the distance between their schools, is 6 miles. Right, so if their house is here, here's their starting point. She's going to cycle. He's going to walk. But we know the total distance they cover when they get to school is 6 miles. Again, here we're noting that we multiply across. But because we have a total down here, that's telling us we get to add on the way down. Which gives us then the equation 1/2 of x plus 7 plus 1/3 of x is equal to 6. I'm going to solve that by multiplying through by my common denominator. My least common denominator is 6, so I'm going to multiply everything in there by 6, which is going to give me 3 times x plus 7 plus 2x equals 36. So 3x plus 7 plus 2x equals 36. That's 5x is equal to, we're getting a little bit of a weird number here. That's what, 29? Oh, that's not right. Lost my mind. Sorry about that. I did not distribute the 3. I get 3x plus 21 plus 2x equals 36. That's 5x plus 21 equals 36. Subtracting 21, I get 5x is equal to 15. So x is 3. Now we want to remember what the x represented. It was the walker's speed. So her brother walks at 3 miles per hour, and she cycles at 3 plus 7 or 10 miles per hour. So hopefully that gives you a structure, a way of solving these 3 fairly classic kinds of algebra problems: mixture problems, interest problems, simple interest problems, and uniform motion problems.